Section 3.7 is on page 226. Talks about curve sketching. A summary of how to graph a function. To really graph a function in math, you need few things, and that's you can graph anything pretty much. Determine the domain. The range is a bit iffy to figure out unless it's something simple like a radical or absolute value, then you know y is always positive, but domain is the key. Range dependent. When the function models a real life situation, make sure you consider the context. Meaning, if they're talking about economics, then normally x is positive and y is positive. And if x is negative, that would mean few years ago. 0 is right now. X being positive means few years from now, and x being negative, that doesn't mean you went back in time. That means you look back at few years ago. Determine the intercepts, that's a key, and asymptotes, those are a must. And then on top of that, the main characteristics of the graph are figured out by the first and the second derivative test. That is, the first derivative test will give you the maximum and minimum, and second derivative test tells you where the inflection point happen and concavity. So to start off, we're going to start with number 2. Analyze and sketch the graph of the function. Label any intercepts, extrema points, and inflection point. Asymptotes is any. Well, this doesn't have any asymptotes. What's the domain? Domain is all real numbers. There's no restriction on the domain. Alright, so what do we do with this? Well, we start with intercepts. If I set to find the y-intercept, that's the easiest of any function. There's only one of those. Replace x by 0, you get a 1. So this is what I know so far. On this graph, the point 0, 1 is an intercept. And to find the x-intercept, you set y equal to 0. And I would complete the square. Students prefer quadratic formula, whatever works. So I'm going to take x squared minus 2x plus a number equal, I'm going to move this to the other side. And if I take half of the middle number, which is squared, out half of the middle term and square it, here it is, I'll get x minus 1 squared equals 1 half. And if I square root both sides, I'll get 1 half under a radical equal x minus 1. So I will get x to be, basically the x-intercepts are going to be, when y equals 0, x will be 1 plus 1 over radical 2, or 1 minus 1 over radical 2. So I could figure out what those are. I know do that, but if you don't, this is about 0.7. So I know this is about 1.70 and 0.30. So about 1.70 and 0.30. Alright, now what? You could use a calculator for that, out of mind. If I take a derivative, wouldn't that be 4x minus 4? Where does that equal 0? That's when x equal 1. Right? I could do my testing there. I could do my testing in my second derivative. Well, let's keep it simple. X equal 1, that's a critical number. This is y prime, this is y. If I pick a point to the left, let's say 0. 0 in there will make that a negative. And let's say 2. 8 minus 4 is positive. So we have a local minimum at 1, and if I plug 1 in, I'll get 1 minus 4, 1 negative 1. Something's not adding up. Let me check really quickly. Oh, nothing's working out. Why is that? I see I messed up. And hopefully you see, this is the good part about working things out properly. Because I put them on the wrong side if you notice. We said this was 1.7 and this was 0.3. Again, if you're not sure how to get that, take 1 plus 1 divided by radical 2, and that gives you 1.7, and go back and make it a minus 0.29, which is 0.3. So there, again, everything should match up. 0.3 is right there, and 1.7 is right there. And 1, -1 is a minimum, and doesn't a minimum look like this? So that's very good. I have a very good idea of how this graph looks. I take the second derivative, that would be a 4. So where does that equal 0? Well, nowhere. It can never equal 0. So there is no possible inflection point, but I could still do my testing. I could say this is y prime. There's no point to test, but if I pick any point, isn't the second derivative always positive? That means y is concaving up from negative infinity to positive infinity. Right? So since I know that, I could say, well, that's easy then. The graph has to go through its intercepts, through that point, and come back up. That's concaving up from negative infinity to positive infinity. So here we want to really get a lot of characteristics out of graphs and figure those out. So we could read all of these economics graphs for profit, for revenue, for cost, and so on and so forth. Next problem up is number 8. Again, we want to sketch a graph of that. Well, let's see. What's the domain? Domain is all real numbers. There's no worry. Range, we're not going to worry about that. So if I find the intercepts, to find the y-intercept, you set x equal to 0. If I put 0 in there, obviously I'll get a 0. Right? This is the y-intercept. That's easy to find. X-intercept, you might have to do some work. Let y equal 0. So 0 equal x to the 4th minus 4x squared. 0 equal x squared into x squared minus 4. 0 equal x squared into x minus 2 into x plus 2. So I have 3 of those. I have 0, 0, I already listed out. 2, 0, and negative 2, 0. So this is what I know. Again, intercepts are really important. They give you good characteristics points of the graph. 0, 0 right there, 2, 0, and negative 2, 0. That gives you a really good feel for the graph. Now, if I take a derivative, y prime is actually 4x cubed minus 8x. And if I set that equal to 0, that's 4x into x squared minus, what would that be, 2? So critical numbers would be where the derivative equals 0. That's when x equals 0 and x equal plus or minus radical 2. So 3 points to test. There's 0, there's radical 2, and there's negative radical 2. Here's where you would benefit more. I'm going to skip this and show you really quick and come back and do it. Here where you would benefit more by taking a second derivative and figure out inflection points. And I'll show you. If I take another derivative of this, that would be 12x squared minus 8 equal to 0. That's when x squared equals 8 over 12, which is divided by 4. That's 2/3. So I figure that I have possible inflection points at square root of 2/3 and negative square root of 2/3. If I want to pick a point to the left, let's say negative 10. Negative 10 squared, negative 1200 minus 8 is positive. So, let me to squish things. I'm taking negative 10 as a test point. This is y double prime, this is y. I pick 0, which is between a positive and a negative. If I put 0 in there, I'll get 0 minus 8, which is negative. And if I put in a point to the right of right, let's say 10. 10 in there, that will make it a positive concave up. Now, do we agree that negative radical 2 is in there? And if you're not sure where that point is, you could plug it in your calculator and figure it out. You could take the square root of 2 divided by 3. It's 0.8. Right? And for those of you that don't know, radical 2 is about 1.4. There you go. So, a point to the left, I notice that radical 2 is in there. Isn't that a minimum? So we know we have a minimum at negative radical 2. I'll figure that point out in a minute. And do we agree that 0 is right there? Isn't that a maximum? Max at 0, I'll get that in a minute. And we have one more point to really consider. You know what? I'm going to push this up and make this more spacious. Here we go. Push those up a bit. This way we're not squishing. And wouldn't radical 2 be in there? That makes that a minimum. So we have a minimum at radical 2. Now, I need to figure out the points. I don't mind you using the calculator and approximating those. If you take radical 2 and you put it in there, if you take negative radical 2 to the 4th minus 4 times radical 2 squared, this will be a 2. This will be a 4 minus 4 times 2. That will be a negative 4. This will follow. And if I put a 0, I'll get a 0. So I have a maximum at 0, 0. I know what maximums look like. Maximums look like this. And I have a minimum at negative radical 2. Negative radical 2. This is negative 1, negative 1.4, 1, 2, 3, 4. And a minimum looks like this. And another minimum at radical 2, 1.4, 1, 2, 3, 4. So those turn out to be a lot closer than I anticipated, but that's okay. There. Now, I do have an inflection point, and that's going to be a main point. I do have an inflection point at negative radical 2/3 and radical 2/3. Well, let's see how that plays. I have a calculator. I could plug it in and figure that out by hand if I really want, right? You could plug it in a calculator. You could say, if I take negative radical 2/3 to the 4 minus 4 times radical 2/3 squared, that is 4/9 minus 4 times 2/3. That is all over 9. That's a 4. This is 8 times 3. 8 times 3 is 24. That's negative 20 divided by 9. That's negative 2 and some. So radical 3 over 2, we said if you take, that's 0.8, right? Radical 2 divided by, 2 divided by 3. By the way, you could do this if you want. Radical of 2/3, it works the same way. 0.8. So this is about 0.8 and negative 0.8. And the y, 20 over 9, again, that's 2 and some. 20 divided, that's 2 and 2/3. That's 2.2. So, if I go to 0.8, negative 2.2, and negative 0.8, negative 2.2. That's an inflection point. Well, we know now how the game is played. if I really play it right, inflection point concaving up, that's concaving up. Concaving down, that's concaving down, right? It's supposed to continue, and that's really how we see. And then concaving up again, from this point and on, that's concaving up. And if I connect this with a smooth curve, that's how the graph looks like. So the graph doesn't work much without the work. Make sure you could show the work on those. They're lengthy, not to worry. We're not going to have a whole bunch of those. Just going to practice a bit. Again, this is going to reinforce what we learned about graphs. Next problem up is number 14. And the same deal. 1. We have a vertical asymptote at x equal -3. That's crucial. We know a graph gets very close to the asymptote but never reach. So -1, -2, -3. This red line we're going to get very close to but we can never reach. Now, if I take, that's the domain basically, it's right there, right? If I take the intercepts, y-intercept, if I replace x by 0, 0, 0, 0, that's 7/3. 0, 1, 2, and 1/3. Again, you could use your calculator to figure out where that is. And how about the x-intercept? How about the x-intercept? If I set the top equal to 0, where would x squared plus 4x plus 7 equal 0? And let's see how that works. That's when x squared plus 4x plus a number equal -7. Take half of the middle number, which is 2, and square it. This is x plus 2 squared equal -3. So none. The graph doesn't cross the x-axis. Very good to know. Now what? First derivative test is not going to be as simple as before, but it's okay. We could handle it. Let's go with the first derivative test. If I take y prime, that is derivative of the top times the denominator, minus the top times derivative of the denominator, all over the denominator squared. So now I really have to clean this. I have no choice. That is 2x squared plus 4x plus 6x plus 12 minus x squared minus 4x minus 7. A lot of work. Y prime is x squared, 4 plus 6 is 10. 10 minus 4 is 6x. And 12 minus 7 is a 5. And my first derivative test, I noticed that equals 0. When x plus 5 into x plus 1 equals 0, that means x would be a -5 or a -1. And where does a derivative not exist? When x plus 3 squared equals 0, that would be when x equal a -3. So my test points, I have to test around a -1, a -3, and a -5. And if I take -6 as a test point, the denominator is always positive. But if I put a -6 right there, that's a negative times a negative, that's a positive. If I pick a point between -3 and -5, let's say -4. -4 plus 1 is positive, negative, that's a negative. Between -1 and -3, -2. -2 there, that's positive. -2 there, that's negative. and a point to the right of negative 1, say 0. 5 times 1 is positive. So this is up, down, down, and up. So what we know right now, we have a local max at negative 5. I'll get that point in a minute. We have a local min at negative 1, and let's see. If I plug in negative 5 up there, again, I don't have to do that by hand. I can say parentheses. Remember how this works? Negative 5, enter, and we're going to go in and use answer squared plus 4 times answer plus 7 divided by answer plus 3. I'll get a negative 6. And if I go in and figure out where negative 1 is, so negative 1, enter. If you recall, we go back, and that tells us that 2. So we have a local maximum at negative 5. Let me shrink this. It's not going to fit. So let's restart. I have a vertical asymptote at negative 3. I have an intercept. The graph must cross through its intercepts 0, 1, 2, 3, 2. And I just figured out that we have no x-intercept. We have a maximum at negative 5, 1, 2, 3, 4, 5, negative 6. Maximums look like this. And we have a minimum at negative 1, 2. Negative 1, 1, 2. A minimum look like this. Okay, very good. Actually, I have a very good idea of how this graph looks, right? It has to run next to the asymptote, right? And it goes through this. Now, I'm not sure whether the graph continues. This is the part I'm not sure about. Does the graph continue up this way, or does it continue this way? And here, does it come down, or does it, and that's where concavity comes in. And let me do the concavity, and that should really tie the knot on this. So I need to take y double prime. Okay, if I take the second derivative now, it's right there. The derivative at the top is 2x plus 6 times the denominator minus the top times derivative of the denominator all over the denominator squared. Gives you a big mess. If I factor x plus 3 out, I'll have a 2x plus 6 times x plus 3 minus x squared minus 6x minus 5 all multiplied by 2. Oh, I should have paid attention to that. Okay, I'll do it in 2 steps. Minus 2 into x squared plus 6x plus 5 all over x plus 3 squared. This cancels one of those, and I'm looking at y double prime equaling, and that would be 2x squared plus 6x plus 6x plus 18 minus 2x squared minus 6x minus 5 all over 3x. X plus 3, those cancel out, I'm left with 6x plus 13 over x plus 3. Now, if I do my testing for this, I just have to worry about negative 3, negative 13, oh let's see, I have negative, where does the derivative equal 0? Derivative equals 0 when x equal negative 13 over 6, which is 2 and some, and y double prime does not exist when the denominator equals 0. So if I do my testing, negative 3 is to the left of negative 13 over 6. And if I use my calculator, figure out where 13 divided by 6 is, that's negative 2.16. Okay, so this is y double prime and this is y. If I pick a point to the left of negative 3, let's say negative 4, negative 24 plus 3 is negative, negative 3 minus 4 is negative, that will be a positive. And if I take a point between negative 3 and negative 2, how about negative 2.5? Again, I have a calculator. I could take 6, so negative 2.5, I could take parentheses 6 times answer plus 13 divided by answer plus 3. Negative, that's all I care about. And to the right, let's say 0, that's 13 over 3, which is positive. So the graph is concaving up from negative infinity to negative 3. Okay, something's not right. Something's off with my numbers. I must have messed up on one of the signs. And I see it. I see it right there. I made a mistake. That's a negative 2x squared minus 12x and a minus 10. See, the calculus and the graph must match. Those do cancel out. I'm left with those cancel. Oh, I'm left with just 18. Look at that. See, all of that work is not needed. Again, the beauty of you always checking, does my answer make sense? So I only have to worry about one point, the negative 3, that's it. So if I pick a point to the left of negative 3, let's say negative 4. That will be positive over a negative, which is a negative. The graph is concaving down. And if I pick a point to the right of 3, say 0, 18 over 3 is positive 6. So negative 3 what? There's my equation. Oh, negative 3 is not part of there. So that's not an inflection point, actually. But the graph is concaving down, indicating the graph looks like this. Now that I know the graph is concaving up, I could continue this. And now that I know the graph is concaving up, I know the right side looks like this. Otherwise, I would have gotten an inflection point there and I figured that out. So, I'm not going to overwhelm you with problems. I'm going to give you as much as I did. Maybe one more. And there's our homework for this section. I just want to do those 4 problems. There's only one problem with